Welcome to the FOQUS usage guide, and for this video we're going to show you how to perform optimization in FOQUS. So the first thing we're going to do is we're going to go to our session homepage and we're going to call this session name usage_example, and we're going to save this file in our desktop. Alright, so afterwards we're going to go to our flow sheet and create a new node. I'm going to call this node my_node. And next we're going to open the node editor, and we're going to insert 4 input variables. So we're going to call these A, B, X, and Y. And we're going to set the default values as 5 for A, -2 for B, 3 for X, and 4 for Y. And for the minimum maximum values, going to set each of them as -10 and 10 respectively. Afterwards, we're going to go to our output variables and insert an output variable Z. Then we're going to go to our node script and insert the equations relating Z to our input variables. So we're going to go f of Z is equal to x of A times x of X plus x of B times x of Y. Then we're going to go back to our variables list and click the default button in order to change these values for our input variables into their default values. So we're going to click yes, and there we have it. Then we're going to save our flow sheet by hitting Ctrl S on our keyboard. We can continue, and then we're going to run this flow sheet to make sure that it works. And so the simulation has finished almost instantaneously, and if we go to our output variables, notice that the value of Z changed from 0 to 7.0, which is the correct answer. So to perform the optimization, we need to go to the optimization tab, and here we see the screen where we have the variables tab here open. So we're going to specify variables A and B as fixed, or constant values in other words, but we're going to make variable X and Y as decision variables that we are going to vary in order to optimize our function. So the other tab that we have are samples tab, and in this case we don't have any samples, but these samples page can be used in cases where we're performing optimization under uncertainty, and we will show you how to perform this procedure in a later video in the series. Okay, so the next step we're going to do is we're going to go to our objective function, and we're going to type in our objective function as a simple Python expression. So to insert a new objective function, we click the plus button, green plus button here, and we type in our expression. In this case, one of the easiest things we can do is if we go to our variable explorer and we go to my node, click the arrow, and then we click the arrow next to my node output, and we select my node output Z, and we select this set of code, hit Ctrl C for copy, and then we close this, and we double click this and hit Ctrl V for paste. So now we have our expression here, which is Z. And it is important to note that FOQUS performs minimizations for optimizations, and therefore if we would like to maximize this function, we need to add a negative sign in front of the expression. However, because we would like to minimize this function, we are going to remove this negative sign. So for penalty scale, we are going to put in a value of 1, and for the value for failure, we're going to put in, let's say, 100. And this is the value that appears whenever the simulation fails. Okay, now we're going to also insert a constraint, and to do that we need to click on the green plus button here next in the constraint box. And it is important to note that in FOQUS, all constraints must be of the form whatever your expression is, which is less than or equal to 0. So for this example, we have our constraint, which is x minus y is less than or equal to 5. And in order for FOQUS to understand our constraint, we need to convert it so that we have our expression or equation less than or equal to 0. And in this case, if we move the value of 5 from the right-hand side to the left-hand side, we end up with x minus y minus 5 less than or equal to 0. And this is what we're going to type up in our constraints box in FOQUS. So once again, I'm going to go to our variable explorer and go to my node here and click on input. And we're going to select x, and we select this expression, hit Control C, and then we hit escape to close the dialog box, and then we go to our expression, hit F2, and hit Control V to paste. And for the case of y, we are going to simply type it in. So we're going to say x square bracket, and then quotation marks. So my underscore node, and then y, and then we're going to put in minus 5. And this, if you notice, is the same expression as one we have here, x minus y minus 5 less than or equal to 0. So in this case we have x minus y minus 5 is less than or equal to 0. And for our penalty factor, we're going to select 1, and we're going to select the default value, which is fine in this case. Then the next thing we're going to do is we're going to go to our solver. And for this example, we're going to select NLOpt as our solver and select Bobika. And all the defaults are fine, but we're going to make the tolerance more lenient to 1 times 10 to the negative 6. And if you make the tolerance more lenient, we can make the simulation run faster. And this is why we are doing this. And these are the tolerances for the absolute and relative differences between the output variables and input variables between iteration to iteration. So in this case, this is the value of our output variable z from previous iteration to the next iteration, and how much our tolerance is, so how close they need to be before we stop the simulation. And likewise for our input variables x and y, we also want to see how close they have to be before we stop the iteration. So I think these values are fine, and the rest of these are fine as they are for these settings. So we're going to go to our Run tab here to run our optimization. So first we're going to save the file by hitting Control S and clicking Continue. And to run the optimization, we simply click on the green Start button. And as you can see, we have two graphs here, which shows information regarding the optimization. So this first graph shows the values of our decision variables x and y, and their normalized value going from 0 to 10. So a value of 0 here means that we are at the lower bound for this value of x, while a value of 10 here means that we are at the upper bound for the value of y. Likewise, we also have another graph here which shows the value of the objective function, which is z, versus the number of iterations. And as you can see, the dots here are all lined up, which means that we do have convergence. And this table here shows the values of our decision variables, and this part of the table here shows values of our objective function. And as you can see, after 23 iterations, the minimum value of our objective function has been reached, which is negative 70. Likewise, we can see the values of our objective function and the decision variables. So we go to variables here, we see the optimized values of our decision variables x and y, so which is negative 10 and 10. And if we go to our flow sheet and open the node editor, and we go to our input variables, we see that the values of our objective function has been changed from negative 10 and 10 for x and y, and output variables has been changed to negative 70 for z. And we can also view the results in a tabular format. So if we click on the flowsheet table here, and we can see that the results are shown on this table. So this is our run that we did to test to make sure that our node is indeed running properly, and these are the values that we get for our optimization. So what we're going to do is we're going to go to menu, go to export and select copy data to clipboard. Then we open up Excel and paste this by hitting Ctrl V. And we don't really need this information for a single one, so we're going to simply delete this. And meanwhile, we're going to make these cells wider. Okay, so for optimization, we have these results here. I'm going to freeze the panes. So we have the values of A and B, which are fixed to 5 and -2, and the values of X and Y, so the initial values are 3 and 4. And if we keep scrolling down, we do have -10 and 10. And then we have our optimized value of -70. However, just to be sure that we're on the safe side, sometimes the optimized value may appear in the middle of the optimization instead of at the very end, so it doesn't hurt to check. So one of the things I like to do is to minimum. And as you can see, the minimum is -70, and as another test, we could also perform an if statement in Excel where we check whether or not this equals to our minimum value. And if so, we set this equal to 1, otherwise we set this equal to 0. And we simply copied this over the entire row. And then we can also do a conditional formatting. So let's say if it's equal to 1, we make this green. And as you can see, the optimum solution appeared twice. So the first time in the middle of our optimization and the second time at the end of our optimization. So our optimum solution is -70 for Z, which is our objective function, and -10 and 10 for X and Y, which are our decision variables. And it's also important to note that for the optimization results to be valid, the errors here must be equal to 0, which means that we have no error in the FOQUS simulation. And in this case, yes, they are equal to 0, which is great. Which means that these results are indeed valid. And sometimes it also doesn't hurt to make sure that our constraints are not violated. So what we could do is we perform another calculation here where we have this equal to X minus Y minus 5. And if you recall, X minus Y minus 5 must be less than or equal to 0. And in this case, these numbers are all negative, which means that our constraints are not being violated. So it's also another good news. So not only did FOQUS run all these successfully, but the constraints are not violated in any of these iterations, which means that our optimization results are indeed valid. So this concludes our tutorial for the optimization in FOQUS, and thank you for watching.